Welcome everyone to this fourth edition of our webinar series on optical coherence tomography. My name is Michael Leitner and I'm Product and Sales Manager for OCT at Thorlabs. During the first three webinars on OCT, we already had a look at the basics of this optical imaging technology. We discussed the main differences between spectral domain and swept source OCT. And we had a very interesting presentation given by Dr. Brendan Kennedy from the University of Western Australia, who introduced us to optical coherence elastography, which he uses as a means to gain more contrast from tissue samples compared to what is possible with standard intensity-based OCT. These three webinars can be found on our website at www.thorlabs.com/webinars or on the Thorlabs YouTube channel. Today we will talk again about additional contrast mechanisms and put our focus on the evaluation of birefringent materials. So in standard OCT, we send light into a sample and simply look at the intensity and the traveling times of photons that are back reflected. Besides this, however, there is much more that we can do. For example, we can combine OCT with other imaging technologies and get multimodal and therefore complementary information. In terms of functional OCT, we can have a look at sample-induced changes in the spectrum. We can look at the phase or temporal intensity variations. What happens, however, if the sample is birefringent? So, for example, if there are anisotropies within the material due to inherent sample characteristics like in fibrous tissue or induced by stress or strain. By analyzing the changes in the polarization state of the returned light, we can learn more about the birefringence characteristics and thereby detect and image features that are really invisible to standard intensity-based OCT. Now it is a pleasure to introduce my dear colleagues, Dr. Pablo Stickar and Dr. Matthias Pues, who will share their insights on the fundamentals of this very interesting topic. Dr. Pablo Stickar graduated in physics at the Instituto Balseiro in Argentina in 1992, and afterwards developed signal processing algorithms for NDT systems in the steel industry. From 2007 to 2012, he wrote a dissertation in material science at the ETH in Zurich in Switzerland, and he is now part of the team that develops software and firmware for OCT systems at Thorlabs. Dr. Matthias Pues studied physics at the University of Hamburg in Germany and graduated with a diploma in 2010. After obtaining his doctorate, which focused on micromagnetics, he joined Thorlabs' OCT applications team in 2015, and currently he is responsible for OCT development projects for OEM. Please note that questions can be posted throughout the whole course of the webinar in the Q&A section, which you can access through the icon on the top right of your screen. With that being said, I would like to hand over the stage to you, Pablo and Matthias.
Thank you, Michael, for the kind introduction. And hello, everyone. Today we are going to cover this agenda. We start with a review of the image-based OCT. Then we move to polarization-sensitive OCT, and we cover both the working principle and what happens when we measure and understand an sample. And then at the end we present our proposal. So let me start considering the interferometer sketched on the left. The light from the light source comes to a beam splitter and split in two different directions, to a reference mirror and to a sample that are located at about equal distances, but not that equal because the sample here is moving to show the effect. Then both reflections reunite and go to a detector that is a bit more complicated than the one that is pictured here. It can distinguish between different wavelengths. And what happens at the detector is that we see an interference pattern that whose actual constitution depends on the relative distance between the reference mirror and the sample. We can change coordinates from wavelength to wave number, and an additional mathematical trick allows us to compute the depth profile. The peak of that depth profile is located at the position. The position is actually saying us what's the difference in distance between the reference mirror and the sample. And this is, in this case, it's an opaque sample with only one reflection. It can be also made with a sample that has two different reflecting surfaces. The spectrum is a little bit more complicated, and the depth profile shows us, in this case, two peaks. And for example, this can be used to measure the thickness of a sample, but there are also a lot more interesting applications, as will we see later on. These theoretical ideas are not just theory; they can be made reality. That have been done at Thorlabs since many years. You can find the details in the webpage that Mikhail mentioned, or in the webinars in a much more didactical way also. But what happens if I take one of these instruments and make a measurement? And I will take one particular instrument, the Telesto 221, with a central wavelength in 1300 nanometers and a resolution that is 13 micrometers lateral or 5.5 axial. To make a measurement, I need a sample. And I will take a very common object that everyone here already knows, Scotch tape. It looks turbid, but it's, if you apply it, it looks invisible, as they say. But we will use the roll without applying it anywhere. And it is ideal for near-infrared OCT. Then we have to define where we are going to measure. We are actually interested in obtaining a cross-section, as shown here in the sketch. We will be illuminating the sample from above at the different positions. So we are not going to make just one depth profile, we call it A scan, but many of them, and that will be a B scan. So we just position the sample below the scanner. That's the scanner is the device that hangs above the sample. And once we adjust everything, then it takes a couple of clicks to get a picture, or actually the cross section. And so the picture that appears here down right is the cross section that is sketched here on the top. And yep, the picture shows clearly the many layers that are inside. I think nobody is surprised that a roll tape, tape as this one has many layers. I selected here a rectangle, and I made a depth profile averaging on that rectangle. I get the curve that you see on the left. The many layers can be clearly distinguished, also the position of the glue. The only detail that catches the attention is that there's kind of a valley here around 1 point something millimeter deep. We will get back to this detail later on. But well, okay, now that everyone kind of remember what is image-based OCT, then we move to the case of polarization-sensitive OCT. So we start this saying, okay, how we build the interferometer in that case. And to do that, I will use some graphical notation. On the top, on the center, I show what I call parallel polarization, linear polarization. At the right top, I say that's the perpendicular polarization. And they both can be combined in many different ways. But for example, here at the center bottom row, I just add them exactly in phase. And a detector that is here at the front will measure the superposition of both. Also a linear polarization state, but in a different direction. and both situations on the bottom row cannot be distinguished by a detector that's located at the front. That this superposition, or the other way around, that the composition is very practical for us to make that, this abstraction and understand how things work, but the detector cannot see that. We can combine these two exactly in phase, or we can shift one to the other. For example, if I shift one of them a quarter of a fourth length, of a fourth of a wavelength, excuse me, then what comes out is circularly polarized light, and again a detector at the front cannot distinguish between both situations. If the displacement had been a different one, not a fourth of a wavelength, but a different one, then what we get in general is elliptically polarized light. This is not just theory, it can be used actually in practice. Let's say we use a wave plate, or also called a retarder. And in this case, with two principal axes, the slow axis and a fast axis. And we have, in this case, to show the effect, incident light from the top left is linearly polarized at 45 degrees. And so both components are exactly in phase, but then the component that is parallel to the slow axis will get out delayed with respect to the component that is on the fast axis, parallel to the fast axis. So as a consequence of that, I will get circularly polarized light. And this is the trick that we need to build the equipment. We begin that by making the reference arm. And in that case, we will use parallel incident polarization. It will emit a quarter of a plate tilted at 22.5 degrees. And then the outcome will be elliptically polarized light, which will be reflected exactly the same as elliptically polarized light, but in the other direction, and will pass once again through this exactly the same quarter plate, and it will emerge as linear polarized light, but at 45 degrees. And I draw both ways separate, but they're actually on the same line. Okay. Then we add the sample arm, and we use a second quarter plate here with located at 45 degrees. And in this case, the parallel incident polarization will be transformed into circular polarized light, will be reflected as circular polarized light in the opposite direction, and again through the same quarter plate, and will emerge back out as perpendicular polarization. Then both this perpendicular polarization from the sample arm and the 45 degrees tilted polarization from the reference arm will combine together at the beam splitter and build an interference pattern. In this case, I'm using a sample that is just a mirror. A more complicated sample will come right afterwards. Now, the thing is how this interference pattern is built. And actually, one question that comes here is why do we have a 45 degrees tilted quarter plate and another one at 22.5? So the situation that we have here is the center top, and then the reference is at 45 degrees, emerges on the sample at 90 degrees. One could ask, okay, if both were at 45 degrees, then the interference pattern could be stronger. But if the sample is birefringent, it's not just a mirror, then the sample will also produce part of the signal in the other axis. If the reference is at 45 degrees, then it may build interference pattern with both of them. If both quarter plates were tilted at the same angle, then that could be impossible. So we build the rest of the equipment. We need a light source, of course, and we need also a polarization maintenance circulator. This one is a device that takes light in one port and takes it out in the next port. And the light that comes with the interference at this port will go will get directed to a polarizing beam splitter that allows us to divide the signal in parallel polarization and perpendicular polarization. So we read out the information at two different detectors that work simultaneously and with the same distribution of wavelengths. These ideas have been published long ago, and this is the basis of our equipment that we made in exactly the same box, in exactly the same look from outside, the same easy of use. Now, I want to mention that this is not the only possibility. There is PS-OCT is an active research area. We have learned a lot from this community. We will continue to learn a lot from this community, and they do also more complicated things. Let me mention just two of them in which they obtain even more information from the sample. Of course, they all use a light source, a sample, and a range of detectors that allows them to distinguish between both polarization states. But the difference is that that they use more than one illumination state for the incident light. On the left, they use, for example, a polarization modulator to make a sequence of two polarization states. On the right, inside this Mach-Zehnder interferometer, they use multiplexing to get two polarization states in a single sweep. More interesting than describing the working principle is actually working with a PS-OCT, and Matthias will describe that part.
Yeah, thanks, Pablo. So let's have a look again at our Scotch tape, but now with the PS system. So we're using in this case also a telesto, but the PS version of that. So it runs at the same central wavelength, 1300 nanometers, and has the same lateral and axial resolution. But now we have two individual detectors, and we can generate OCT images from both of them. And we call them camera 0 and camera 1. And the cross-sectional image of the Scotch tape looks quite similar compared to the standard system. Again, we see this dip in signal intensity at a certain depth. But for camera 0 and camera 1, these dips of signal loss are at different depths. Here it's in the middle, and for camera 1, it's at the top and further down. If we combine those two, we get an image that we call total intensity, and that's an image that doesn't show these effects anymore. And if we compare the profiles taken from the middle here, we also see the dips in camera 1 and camera 0, but for the total intensity, we get what has been expected, nearly linear signal decrease caused by light absorption and scattering in the sample. So if we take a closer look at the information from camera 0, we have first reflection from the top surface, and then further down, for each voxel of the sample, the light is reflected partially, so we can actually get a signal in our OCT system. But also for each region of space the light passes through, the light is modified by the sample. And the polarization, as we expect, is also changed the deeper the light penetrates into the sample. And if we look at that in a more abstract way, we have our circularly polarized light generated by our system, and that's hitting, say, the first pixel or the first region of space of our sample, and the sample is assumed to be birefringent in this case, so it changes the state of the light by a little bit. And for the next voxel, the polarization is changed again by the sample, and again for the third region here in this case. However, as OCT is a reflective method, we need to have some light of coming back into our detector, and that's what we're considering here at the bottom of the third region of the third pixel here. So the light is partially reflected, and the reflected light is going through the same region of space. So the polarization state is changed again by the path outward. So we're collecting the inward path and also the outward path and what the sample does to the polarization state. And only the result here, the light's coming back out, is going back into our system, and then it's creating an interference with the reference light and is going into our detector, and we can analyze this interference pattern to generate our OCT images. So comparing the information of camera 0 and camera 1, it's, well, we can have a look at the first surface, and we see that for camera 0, we have a very strong signal, and for camera 1, it's a little bit dimmer, and also the first top region here, as we've seen in the full images, is pretty dark. And this, if we remember what Pablo has told us in this schematics, that probably the light that's coming out here and is detected mostly by camera 0 is perpendicularly polarized, and the light that's coming from the dark region here is tilted by exactly 90 degrees, so it's not able to generate any interference pattern with that part of the reference beam. And that's also what's probably happening down further in the sample, that the light that's coming from these bands that we've seen where the sample is getting very dim in the images is tilted by exactly 90 degrees on the way down and on the way back, so it can no longer generate a good interference pattern with the respective reference arm. But can we really say what's going on in these pictures? We're only looking at the intensity images, and it's not really clear what's happening here. So we need another way to represent the information. And for that, we can go to represent polarized light in terms of the Stokes parameters. The Stokes parameters were introduced quite a while ago, and they represent the different polarization states in these three vectors here, the Q, U, and V, where Q is linear polarized light at 90 degrees and 0 degrees. U is the ones linearly polarized light per 45 degrees to that, and V is left and right circularly polarized light. If we draw that as a vector at the origin here, if we have fully polarized light, the sum of all that is 0. So the vector is pointing to the surface of this unisphere here. And if the vector is shorter, it's not fully polarized light. So we can also compute images for these three parameters, Q, U, and V. And we also can see our tape here again, and we see that in the Stokes parameters that they show a continuous dependence over depth. And we also see that in this profile here, where we have this continuous dependency that gets a little smaller with depth, as expected, with that we have some signal degradation because our intensity is not as great the further we penetrate into our sample. And we can already assume that our Scotch tape is birefringent, but having to look at three images at the same time to really see what's going on in our sample is not really handy. So we can introduce two other parameters that are well known for birefringent materials, and that is retardation and the optic axis. The retardation and the optic axis describe the birefringence of the sample, and we can use the information, the intensity of our two detectors or the Stokes parameters to compute these two to describe the properties of our sample. In tissue, the birefringence, for example, is a consequence of its anisotropy, or as Michael has described before, for other plastic materials, it's also caused by stress or strain in a certain direction that is then connected to the optic axis. We used quite simple sample and phantom that has been described in this paper here, and that is polycarbonate stripes that have been stretched under certain conditions. And if you stretch that, you induce birefringence in a very controlled manner. And we cut that up and stack that to have a thicker sample and scanned across these stacks of polycarbonate stripes with different induced birefringence. So you see that image here, and that's the line where we scanned also our OCT beam. And in the total intensity images, all these stacks look identical. However, if we have a look at the retardation image, we can clearly see that the left stack here is left unchanged. There is no birefringence in that, and the birefringence, or the retardation in this case, increases the further we have stretched the stripes. And if we take a profile again here, we can also see this arctangents relation of the retardation. And for the stripes with higher retardation, we can also see that in the profiles. But that was still a pretty simple sample, and let's move on to more realistic samples. And one that is easily available is, for example, my hand. So I have a small scar here on the back side of my hand, and I marked it so I can find it in our scanner again. And I used the scanner here to put it on my hand and find that spot and move it into focus. In our software, that looks like this. So on the bottom right here, we have a video monitor where we see that spot, and we can now, if it's more in focus, already see this tiny scar here. And I've selected 2 image representations, and that is on the left-hand side here, the total intensity. So our usual OCT image, where we see the top surface and then the deeper layers in a cross-section of my skin. And in the middle here, I've selected to show the retardation image. And then I can change the contrast setting a little bit, the color scales, so we're not distracted by the noise floor so much. And you see that the retardation it has a lower signal-to-noise ratio compared to the total intensity image. And to improve that a little bit, we can just do simple lateral averaging, and I select now here a kernel of 3 by 3 pixels, and you see that the contrast or the signal improves, especially in the regions where we penetrate deep into our sample, where also the total intensity gets close to the noise floor. And another method that was already applied here and that I'm changing now a little bit to adjust it is thresholding. And that is to combine the total intensity image with the retardation, and wherever we have very low intensity signals, and so we expect no meaningful polarization information, we just threshold that information here in the retardation image and set that to black. And then we can just take a snapshot and store the data for later analysis and maybe post-processing. So let's have a look at the results again. So I've taken a cross-section image here on the back side of my hand where I have a tiny scar, and in the total intensity image, we maybe see a small bump in the top surface, but we don't see structural differences in the scar tissue compared to the healthy tissue surrounding it. But if we have a look at the optic axis and retardation image, we clearly see the scar tissue in the middle and the healthy tissue surrounding it. And that can be explained by the fact that collagen is birefringent, and collagen is regrown in different structure in scar tissue than in the healthy tissue surrounding it. And that's also a method where PS-OCT is used quite often. That is that we can't really see the individual collagen fibers themselves because they are below the resolution of this OCT system. They are too small, but their birefringent properties can be analyzed by our PS system, and so we can have a look into our sample and get more information out of that. Just by looking at this dimensional cross-section, we're not getting a full picture of what's going on here, so it's always good for these three-dimensional images to actually take a whole volume of OCT data, and that's what's indicated here in the red square here. And if we zoom through this volume stack of the retardation image, we also see the scar here quite clearly in the picture. Another tissue type that we can test is chicken tissue. So I just went to the supermarket and bought some chicken thighs and selected here this spot that looked quite interesting to me. So where we have some fat tissue on the right and some membrane in the middle and muscle tissue on the left. For the total intensity, we also see that there are clear structural differences. The fat is this sponge-like structure. Here, the membrane is highly scattering, and if we look more closely, it also has some substructure to it. And on the left-hand side, we can see this little darker muscle tissue. But if we look at the optic axis and retardation image, we can see that there's even more going on. So the membrane is not this whole mass here, but it has a clear top surface structure. So it's layered, and below there's a different structure. And the region on the side here that seems to be the same as the one in the middle here is clearly not the same in the retardation image. And if we take a look at a volume scan, we can also see that on the membrane here, we have some stripes that are oriented in this way. And the region that I indicated, that I show here, has also some stripes, but they are oriented just 90 degrees to those in this region. Of course, this is just an easy example, and we can't really say if the polarization effects in our sample are intrinsic to the sample tissue, or if we have induced them by stressing it and cutting it up and placing it on our sample tray to investigate it. These colors, these images are still pretty colorful and full of information. And there is another way that has been used quite often and that we have also implemented to reduce the amount of information a little bit. And that is to look at the degree of polarization uniformity. That is a parameter that looks or that can show you how depolarizing your sample is. And one good sample for that is teeth. So we've taken a tooth here, and the tooth has some carious lesions that you see here in this white bright spots. So we're scanning along the red line here again. So we have some healthy tooth that is highly structured tissue normally, with crystalline structure even to take up the load of daily use of the tooth. And then we have the regions where bacteria have, well, eaten away the tooth, and the body is trying to remineralize that. But this remineralization process is not getting back the ordered structure. And the structure is depolarizing. And in the total intensity image, we see the healthy part here. And we also see a little difference on the left-hand side where the carious is. And on the optic axis and retardation image, we also see this behavior, but the optic axis is showing in this region very irregular signal, and it's quite random, to be honest. And if we have a look at how the degree of polarization uniformity is computed, it's taking a spatial average of the Stokes vectors to see if they change a lot, and that is an indication of depolarization. And we can also have a look at the individual Stokes vector images, and if we combine that, we get this Doppler image. And on the right, there DOPU is quite high, close to 1. So we see that this region is not depolarizing our light, but on the left-hand side, as we have expected, the signal is quite low. So it's easier to look at this image to see where we have regions on the sample that are depolarizing. And we can also see that the surface here is not really depolarizing, so that should be a different structure. Maybe it's still the healthy tooth and the caries has eaten a cavity here from the side. So that sums up our webinar today, and let me just sum it up a little bit, that we've shown the PS system and how it can yield more insight into sample structure. And we've shown some examples from the biomedical field, and there are even more applications in that to look at collagen, for example, or bone or brain tissues. But the other classical applications where OCT is applied can also be used with a PS-OCT system, that is material science. So molded plastic pieces are very well known to have stress induced by birefringence, or quality inspection is also a wide field. In general, wherever there are fibers or structures that are below the resolution limit but have birefringent properties can be investigated by PS-OCT. So we set up a single input state spectral domain PS-OCT system, and our design goal here really was to have a compact benchtop system that can be set up easily and can be used easily. That there is no calibration and adjustment in the day-to-day use of the system. And the system we have is the only turnkey PS-OCT system on the market to this day. It's based on our Telesto series. So again, it's working at 1300 nanometers and has a maximum A-scan rate of 76 kilohertz. I've shown it in use with our compact scanner that we call OCTG, but it can also be combined with our user customizable scanner, the OCTP. And that scanner type allows you to adjust the optical path in the scanner, so to maybe add other modalities like fluorescent imaging. You can also add our standard 3 different scan lenses to change the magnification, so the lateral resolution or the field of view. The system runs with our standard 4-image OCT software that gives you easy access to your sample, so you can already see the PS parameters in live data viewing, which is really handy for recording and analyzing the data. But you also get the full access to the raw spectral data for customized post-processing and further data analysis. And if you need special image acquisitions, for example, you can also use our SDK to control the system through individual codes that we have with C and LabVIEW libraries. And this development, of course, was a collaborative effort from our team that I would like to thank here, and also you for your attention.
Thank you very much, Pablo and Matthias, for these really interesting insights. And we already have several questions from the audience. Shin is asking, I wonder if it is possible to collect fast changing retardation signals, so dynamic changes in birefringence, down to the nanometer scale of the source in the sample.
So if for the first part of your question, in terms of time, of course, the well-known A-scan rate that's always connected with the OCT systems, and that I mentioned of 76 kilohertz, is only one depth scan. So if your information is spread over a region in space and you need to really take a picture, you need to divide that by the width of your picture. So if you can live with a very small B scan of, say, only 100 lines, you're already getting to a frame rate that is below a second, but it's of course not then in the kilohertz range. Michael, can you repeat the second part of that question?
If it can get to the nanometer.
So I will read the whole question
scale.
again. I wonder if it is possible to collect fast-changing retardation signals, so dynamic changes in birefringence, down to the nanometer scale of the source in the sample.
Pablo? So I think that that we don't have the resolution to distinguish small effects at that scale, but the objects that are generating that birefringence are actually macromolecules in the nanoscale. So that in that sense, if the sample contains many of those macromolecules and they are statistically aligned, then at that point in the sample, then the birefringence will take place and we will be able to measure it. But if you have two close points with two different directions, then it will be not that possible, so not below our resolution.
Thank you. An anonymous user asked, can you provide more detail on the kind of tissue for which we can expect birefringence?
Yeah, so the biological tissue, again, there are macromolecules that are that generate birefringence. I think that the slide number 40, and then in that those macromolecules can will generate the birefringence. The examples of these macromolecules are collagen or microtubules. These are the two main ones. Muscle has also, but it's not that perfect. And the collagen tends to adopt many different configurations, and maybe you need to stretch the sample to make it clear, or in some positions it's there is a clear direction, and then it can be measured without stretching the sample, without making forces.
Thank you. Mylene asked, how sensitive is the alignment of the two cameras regarding the optical path difference after separating the different polarization states?
Well, it's very critical. That's a very critical point when during the fabrication process, and we take everything to make to make that difference below the resolution that we can check. That is critical, that both sensors are aligned exactly the same way.
Okay, thank you. The next question, in slide 52, 53, why do the optic axis and retardation look the same? Can you explain a bit more about the significance of retardation and optic axis, please?
It's the 50 something.
Sorry.
Yeah, so the optic axis says what is the direction of the slow axis. So what is the geometric direction perpendicular to the incident light that is retarding the light, the phase, and the retardation is in what amount is that retarded. Both pictures on the bottom row show similar features because the geometry they refer to is the same, but they are quite different meaning.
Okay, thank you. The next question, can you explain again how from two camera images you calculated Q, V, and U values?
Yeah, I think that we have another slide for that. That is that has our signals, and yeah, exactly that one. What I get from, or what we get from the two cameras, and to compute the depth profile, we actually what we compute are the reflection coefficients along the t-axis on the y deeper and deeper. And from those reflection coefficients, we can reconstruct what's the field, the electrical field, up to a factor. And then to obtain the Q and V, it's just a mathematical combination of them as complex quantities. It's a very straightforward computation.
The next question comes from Joy. The polycarbonate phantom birefringence is dependent on the amount of stretching. Is there any phantom that has inherent birefringence without stretching to calibrate the system with?
Yeah, we've looked also into that, and for PS-OCT, we found that this method is giving us good results. I mean, you can always use the optic components that are well known, like quarter wave plates and other things. However, these are always clear. And for OCT, we need to get some scattering inside of the sample to really make use of that. Of course, you can use much more calibrated quarter wave plates or other clear materials, and then look at the effect on the bottom interface or a mirror that's placed below. But that's only giving you a very sharp line. And of course, in this illustrative manner, it's always better to have a signal that is over depth range. And that's why we use the polycarbonate. But yes, you can use other samples.
The next question, is the light in PS-OCT fully polarized or partially polarized? In terms of the Q, U, and V calculations. Also, do you quantify these parameters in some way apart from visual inspection?
And then it's fully polarized. So the OCT bases on interference, and the non-polarized light cannot build interference, so it's out. So so the signals that we have are actually those that build the interference. So we only use the polarized part of the light. We do just visual inspection to check the Stokes parameters. I'm not sure if I answered the question.
Musa asked, what image quality can PS-OCT provide in terms of dynamic range and peak SNR?
So that's really dependent on the A-scan rate, and it's comparable to our standard telesto systems. So for the slowest A-scan rate, that is 5.5 kilohertz, it's 109 decibels sensitivity, and for the fastest, that's 94 decibels.
The next question, since we split light in the reference arm to P and S polarizations, does this mean our intensity image of combined P and S images is weaker than for a single stronger channel, maybe due to noise addition?
Can you repeat? Excuse me.
Maybe I can start. I think the we can use the fact that for most imaging conditions, we have enough reference light. So we have more than enough reference light in our system that we can also change on the scanner the amount of reference light that we mix into the sample light to go back into our detector, so that we're only using a part of the reference light is not weakening our signal, because we can mix in just a little bit more of light, so our detectors are saturated to the level that we require.
Thank you. The next question, is there a reason why you use Stokes formalism and not Jones?
Well, we're actually using the Jones, or they are similar in this case, because we are not making really an averaging. So it's so we use the signals directly. The Stokes parameters have the advantage that you don't have to think of the phase. The Jones vectors, well, I don't know of a display to put them in pictures, but they're available, so it's very easy to compute them from the raw signals, or using our SDK. You can get them also.
Okay, the next question, how to extract the information of different layers in retardation images based on a threshold of the intensity?
Yeah, I think that you go, Matthias, to this one or this one, or
yeah, let's move to this one. So if we're purely talking about the thresholding effect, we as I said, have a look at the total intensity image, and in this case the threshold was probably set around the lower level that's indicated here, so 35 decibels, and the actual noise floor of the retardation, of course, is by 1/4 of a pi, so represented by blue here, but that's not the case, so we replaced that by black. But I'm not sure if that was the goal of the question. It's maybe Pablo, you can comment on how to extract the individual layers out of this.
Well, just the individual layers is difficult. From these pictures, over several layers, you can think of the slope of this curve. If you need the different layers, then there is a need for more sophisticated algorithms. In the last 2 years, there was a group at Massachusetts General Hospital that showed how to do that in the case that you assume perfect prior refringence in the sample and no attenuation. In that case, but you can do that, but the algorithms is quite different using exactly the same hardware. That could be layer by layer, but if the sample had some homogeneity that you can use, then the slope of this curve will be given the retardance, and this curve is actually rapid. This is why it looks up and down, but it's actually one single curve that started here, goes up, and then this is the way it's going.
Thank you. The next question, do you have some examples for what can cause depolarization?
So maybe you can first start, do we actually have depolarized light? But if you look at the individual photons, of course, they are always fully polarized. So it's really the effect that for very small regions of space, the polarization state that is coming back from the sample is drastically different. And because we have a certain resolution here with our system, we only capture from that region of space or inside of the PSF one particular polarization. And for the tooth here, it's I assume really this sponge-like structure that the carriers leaves behind that scrambles the polarization state on tiny length scales. So it's really what the degree of polarization uniformity picks up here.
The next question comes from Masahiro. Excellent works. It may be helpful if we can know how to interpret the accumulated retardation and axis images, which is very characteristic in the case of depth-resolved polarimetry.
Yeah. Let me consider the following pictures above. In the top row, I have a sample that has actually is always the same optical axis, or it is a uniform retardation. But when I explore only one layer, then I get incident light, outgoing light, and then I can compute what the characteristics are. If I have more layers, but I cannot distinguish them, then I see that the incident light is exactly the same, but the outgoing light is different, so the properties of the material are different. But if as we use an algorithm that cannot distinguish or cannot resolve in depth, then I compute an optical axis and a retardation that is different from the real one. It's cumulative, so the effects accumulate on both ways. And then if I consider a third layer, then the situation is even further so. So this is why actually there is a slope, so there is a smooth change between the different layers. If I had something depth resolved, then it could be in different layers. I could see exactly the same. This is the main difference between cumulative and depth resolved.
Thank you. Next one, how do you calibrate the cameras? So how do you calculate the rescaling function? Do the cameras self-calibrate with each startup?
No, the systems, the cameras do not recalibrate with each go. We have an original calibration, and that one stays. Each camera separately has, yes, a calibration, that because there is a dark current that we subtract, and so there are some characteristics of the camera that we take every time or very often when we make a measurement. But it's actually related also to the way that the light source is changing in time. It is, but the way the cameras are positioned stays the same, and we have checked that stays the same over a long time.
Okay, thank you. Next one, how do you calculate the optic axis from Q and U?
It is, so it's actually Q and U are two numbers between -1 and 1. So they have a sign so that this inverse tangent function can work that out in 4 quadrants. Okay, there is a factor of 1/2. So the result will be in -half p and +half p, which is actually makes sense because we cannot distinguish between a 90 and a -90 degrees rotation. They are both the same to us.
Okay. Can the optic axis information be interpreted as the actual local optic axis at the given depth, or is it an accumulated value over the depth?
We have the accumulated value over different depths. This is what we provide right now. It is. We also provide the spectral data, so the raw data. So more clever algorithms can work that out. We have not that yet.
Okay, and the last one is more a response to a question to how to extract the information of different layers in retardation images based on a threshold of the intensity. So the response is the local retardation difference, not accumulated retardation, can be used to show birefringence layers, which is just the same as the slope of the accumulated retardation, just as the speaker said. Okay, many thanks to everybody for attending our webinar today. If you have any ideas for OCT-related topics that you would like to see discussed, please drop us a message at oct@thorlabs.com. I'm looking forward to seeing you again during our future events and wish you a nice day.